So, we had been discussing regarding the cylindrical wave function and the solution to Helmholtz equation, the source free Helmholtz equation in the cylindrical coordinate system, the solution in terms of rho, phi and z, and what are the characteristics of the so called solutions which satisfy the Helmholtz equation. And we came to this point where the psi can be expressed as a summation over the azimuthal wave number n and kz and summed up over the elementary wave functions. So, let us continue from there. So, we can also integrate over the separation constants, though n, the value of n is usually discrete. This n is usually discrete. So, we will come to that later when we will find that equation number 10 okay, will be satisfied by functions which are in the form of e to the power j n phi. So, which is cos n phi plus j sin n phi. So, it will be usually expressed in terms of the cos and sin terms or a combination of sin n phi and cos n phi terms. So, the value of n will usually be discrete. So, now we can write the possible solution to Helmholtz equation as summation over n integral kz fn kz bn k rho rho h n phi h kzz dkz is equation 14. Okay, so these can also be possible solutions to Helmholtz equations, and here we integrate over the separation constants. Because n is discrete, we express we retain the summation over n and express the summation over kz in terms of the integral over kz. So, we can also express psi as summation over n integral k rho g n k rho b n k rho rho h n phi h k z z d k rho. Okay, so these kinds of expressions are also possible because we appreciate the fact that k rho and k z, these two terms are ultimately interrelated through the equation k rho square plus k z square is equal to k square, which was equation number 8. So, in many cases these kinds of alternate interpretations are very important, because in many cases of the cylindrical coordinates we will find the integration over kz or integration over k rho poses different features. In many cases one formulation can be referred to as the Sommerfeld formulation and another formulation can be referred to as the Shelkunov formulation, and these Sommerfeld and Shelkunov formulations corresponding to integration over dkz or dk rho can have distinct different features when we plot the integrand over kz or k rho, or when we compute the integral, okay, due to different generic forms of fn kz times h kzz and gn k rho times d k rho. Okay, in addition to bn k rho. Okay, so these functions, the combinations of the function fn kz times h kzz, which in this integration kernel is a function of kz. Integration of this function over kz can have distinctly different features than integration over this kernel, which is gn k rho bn k rho times d k rho integrated over k rho. That is why these alternate formulations are very important in the cylindrical domain, though at this point we won't realize their importance. Okay. So, these integrations can be over any contour in the complex plane. They can be over any contour in the complex plane, and fn kz and gn k rho are functions to be determined from the boundary conditions. Now, you might ask me suddenly that where this contour integrations come, because it appears that dkz, dk rho are real numbers. Okay. The concept of contour integration comes because over this integration path, which is integral kz fn kz dkz, there can be singularities of these functions in terms of poles or in terms of other kinds of like more more complex singularities in that form of branch points, which we are not going to discuss at this level. So, because in the path of integration of equation 14, when we are integrating over dkz, we will encounter poles of fn kz times h kzz. We have to deform the path of integration and generalize this integration, real axis integration of kz into the complex plane, and thereby the concept of contour integration comes. Okay, so, we are going to go to the complex plane and integrate over 14 and 15. Okay, so, we will not go further in that direction because it is going to lead us to more advanced treatment of cylindrical wave functions, which are not really part of this course. Now, on the other hand, we are going to focus on the nature of bn k rho and when to use, as we said, the different forms of bn k rho. We already said that bn k rho can have 4 distinct forms: Jn, Nn, Hn1 and Hn2. So, if the field is finite at rho equal to 0, if the field is finite at rho equal to 0, bn k rho must be, it should be Jn k rho. Because all other functions lead to non-computable values, okay, extremely large values as the argument tends to 0. I mean, it can be extremely large values in the negative sense, but they have a singular behavior, that is Nn k rho, Hn1 k rho, Hn2 k rho will have non-computable singular values, okay, as their argument rho or as their argument k rho, okay, becomes 0, because we are dealing with the spatial location, we are not concerned with the behavior of k rho here, our concern is over the rho variable. So, what happens to these functions as rho changes? So, if at rho equal to 0 or the center of the cylindrical coordinate system, the field is finite. In order to describe this finite behavior, the appropriate wave function along the radial direction must have to be j n k rho rho and not otherwise. This has to be very, very carefully borne in mind, because inappropriate choice of functions is absolutely not acceptable anywhere. So, we must absolutely know the proper recipe to use or the proper function to use to describe the wave behavior under the different circumstances or in the different spatial locations. Okay. So, in this case, the elementary wave functions will be of the form psi k rho n k z equal to j n k rho rho e to the power j n phi and e to the power j k z z, rho equal to 0 included. We have already encountered this function before as a solution to equation number 10, and we note that equation number 11 is pretty much of the same form as equation number 10. So, its solution is going to be e to the power j k z z. This equation number 11 is also of the similar type which we meet in the rectangular wave decomposition of the psi function. When we apply the separation of variable to the psi function, okay, or to the psi function which describes the Helmholtz equation in the rectangular coordinate system, we come across exactly the same equation in the z direction and the x direction and the y direction as equation number 11, and its solution is of this form. We are always aware of this, because the solution in the rectangular wave coordinates is either sin kxx, cos kxx or e to the power j kxx. So, we just recall or compare with the rectangular coordinate system where the solutions could be e to the power plus minus j kxx, cos kxx or sin kxx in the x direction. It can be e to the power plus minus j kyy, cos kyy, sin kyy in the y direction, or it can be, I should say, and it can be e to the power plus minus j kzz, cos kzz and sin kzz in the z direction. So, this is the description of the rectangular coordinate system. So, we already know the origin of this function from the equation which is exactly similar to equation number 11 which we discussed here. So, we call this equation number 16. So, we call this equation number 16. So, note that this function on the other hand hn2 k rho rho are the only solutions which will vanish for a large rho if k rho is complex, and therefore, they will represent outward travelling waves. Waves that are going in this direction in increasing rho and include the region rho equal to infinity. If our point of interest includes rho equal to infinity and has to describe outward travelling waves, then this is the only function that can be used to describe such behavior. So, they will represent outward travelling waves if k rho is real. Therefore, if there are no sources at infinity, Bn k rho must be Hn2 k rho if rho equal to infinity or rho tends to infinity, if this region is to be included. Hence, in this case the psi function will become psi k rho n k z equal to Hn2 k rho e to the power j n phi e to the power j k z z, which is equation number 17. So, here rho tends to infinity, the region rho tends to infinity is included. We can also make some qualitative comparisons or qualitative analogies of the cylindrical wave functions. So, j n k rho is analogous to cos k rho, sorry, we can also make some qualitative analogies or qualitative comparisons for the cylindrical wave functions. For instance, j n k rho is analogous to cos k rho, n n k rho is analogous to sin k rho, Hn1 k rho is analogous to e to the power j k rho, or incoming waves from infinity, scattering problems, incoming waves from infinity. Okay. And Hn2 k rho is and Hn2 k rho is analogous to e to the power minus j k rho, outgoing waves. So, now we are armed with finding out the solution to the cylindrical wave equation in terms of the T to Z and Tm to Z modes. So, similar to the rectangular coordinate system where A is equal to u z psi gives rise to the Tm to Z mode, and F equal to u z psi gives rise to the T to Z modes. In this case, the same substitutions made in the cylindrical coordinate systems will yield the same kind of modes, namely the substitution A equal to u z psi in the cylindrical coordinate system will yield the Tm to Z cylindrical modes, and the substitution F equal to u z psi is going to yield the T to Z modes. Okay. However, the cylindrical interface problem is actually more involved than the rectangular problem, because in a rectangular dielectric interface, if this is an epsilon 1, this is mu 1, epsilon 2 mu 2, an incident TE wave in this direction is going to be reflected as a TE wave and transmitted as a TE wave. Similarly, an incident TM mode in this direction is going to be reflected as a reflected TM mode and a transmitted TM mode. Okay. So, this is the nature of the rectangular isotropic dielectric to dielectric boundary. So, this is a boundary between two dielectric media. Okay. Let us continue this boundary. However, the same is not true, unfortunately, for the cylindrical dielectric boundary, making the cylindrical boundary far more complex than the rectangular boundary, which means that if I have a cylindrical boundary here, so if this is epsilon 1 mu 1 and this is epsilon 2 mu 2, incident TE mode is going to give rise to a reflected TE mode as well as a reflected TM mode, and also a transmitted TE or a TM mode, and the similar situation will occur if this is a TM mode. So, an incident TE mode incident at a dielectric to dielectric cylindrical boundary is going to yield a reflected TE and TM types of modes, giving rise to hybrid mode propagation in cylindrical waves or cylindrical dielectric structures. However, the modes are decoupled. We call this a boundary which is decoupled, or we say that the modes TE and TM are decoupled at the planar or a rectangular boundary, whereas the modes TE and TM, they are coupled at a cylindrical boundary. Okay. So, as a result of this, if we want to characterize the cylindrical boundary in terms of reflection coefficients, we have to go towards the reflection matrix instead of the reflection coefficient here, because the reflected field is described only in terms of the reflected TE mode. If you talk of the reflection coefficient here, the question immediately arises, are you talking of the reflected TE mode or the reflected TM mode? So, therefore, in order to describe this complex behavior for the cylindrical wave system or the cylindrical guided wave structures, particularly cylindrical dielectric guided structure, we have to take recourse to the reflection matrix instead of the reflection coefficient, which characterize the planar medium. So, these are the like the distinctions, inherent distinctions between the planar or the rectangular and the cylindrical like the dielectric to dielectric interface. Okay. So, now before we do that, we must also remember that in this case, if this is a PEC boundary, as we are interested in a PEC boundary in this course, if this boundary is a PEC, okay, and this is going to plus infinity and this is minus infinity, the modes TE and TM are decoupled. They are decoupled because this boundary is a PEC boundary or a perfectly electric conductor boundary, as in the case of the circular waveguide. Therefore, in the circular waveguide, the TE and TM modes are decoupled, because this boundary, okay, this boundary and this boundary, the whole thing, I mean it is a single boundary though, it is the whole thing is metallic. In such a case, for the cylindrical coordinate system, the TE and TM cases will be decoupled. But if the same circular waveguide is coated by a dielectric, if the same circular waveguide, if it is coated by a dielectric layer, So, if this is epsilon 1 mu 1 and if this is epsilon naught mu naught in the dielectric layer, inside the dielectric layer the modes will be coupled. So, this will be a very practical problem if I want to have for instance a conformal patch here and fed by a coaxial probe from here. So, the inner conductor of the coaxial probe will be touching the patch through a hole and the outer conductor will be shorted to this ground plane. So, these situations are going to arise in the design and rigorous analysis of all kinds of conformal antennas on cylindrical surfaces, where rigorous mode coupling has to be considered at the dielectric regions, otherwise your analysis is going to be extremely inaccurate. It cannot describe the wave behavior in these regions. So, this is important. However, we are not going to go to such advanced treatments, we will be limited in our analysis to the circular waveguide. Before we go to the circular waveguide, however, we have to, as we said, we have to describe the solutions, the electric and magnetic fields for A equal to uz psi and F equal to uz psi. So, which we will do in the upcoming future lecture. So, let us stop here. Thank you.